Yeah, hi everyone. So this will be the final video of a basic semiconductor physics. So all the concepts are completed, just some miscellaneous concept we are going to see and then we will solve the problems. So first this question was there that let's just consider the case of intrinsic semiconductor. There will be conduction band, there will be valence band and there will be Fermi energy level as well. We can make that Fermi energy level as well. Okay. So there is conduction band, there is valence band and there is Fermi energy level as well. Okay. Between conduction band and valence band there is an energy gap of 1.1 electron volt. In valence band there are bound electrons. At room temperature they are getting an energy of 0.0259 electron volt. How this much energy is more than enough to make a transition from the valence band to conduction band? This was the question, right? Because they need to make a transition of 1.1 electron volt. So how this much energy is enough to make a transition from valence band to conduction band? This is the question. So first let's see it with respect to the mathematics. So what is the probability of finding an electron in the conduction band? What I am saying, what is the probability of finding an electron in the conduction band? So that is given by e to the power minus EC minus EFI, since I am considering the intrinsic semiconductor, right? What do you think, what will be the gap of EC minus EFI? By default I will take it is in the middle, because for intrinsic semiconductor it would be in the middle only. So by default I will take this is in the middle. So this will be 0.55. So what I am getting, 0.55 divided by 0.0259. So what we are getting, somewhat some pretty low value you will get. So you can find it out, 0.55 divided by 0.0259 plus minus e to the power. So you are getting somewhat around 6 into 10 to the power minus 10. This is the probability, not a particular number. This is the probability that an electron can be found in the conduction band. Very low, but it is not zero. You cannot say that sir probability is zero. Although for mathematics you will say sir it is nearly zero only, but still I would say there is a finite probability, there is a non-zero probability, that is 6 into 10 to the power minus 10. A very low probability that any electron could be found in this conduction band at 300 Kelvin. This is the probability that we are getting. But what will be the number of electrons in the conduction band? Why so? Because there will be a lot of states, no? This is the probability of finding an electron on this particular energy state only, on this EC state. But there are a lot of states which is having energy nearly to EC only. So what will be the total number of electrons? Total number of electrons will be number of states multiply with f of EC. This we have already seen, right? Total number of states available, effective density of the states multiply with finding the probability of electron at a particular energy state EC. I am assuming that all these are having the energy of EC only. Although they will have some slightly higher energy, but assuming that all of them are having the energy of EC only. So if this is the probability at EC, then at all of them as well the probability will be EC only. So I can multiply NC with f of EC. There are a lot of states, no? So how many states are there? 2.8 into 10 to the power 19. What is f of EC? 6 into 10 to the power minus 10. Roughly what answer you are getting? Into 2.8 you do 1.67 into 10 to the power minus 9. So 1.6 into 10 to the power 10. So these many electrons you are getting. This would be equal to intrinsic carrier concentration only. So in silicon we say that this is our intrinsic carrier concentration, and by the mathematics we have proven it. So what really happened here was, although the probability that electron will make a transition from valence band to conduction band, that probability is very low, 6 into 10 to the power minus 10, but still it is not zero, and there are a lot of states available. There are a lot of states available for the electron to occupy. That means the number of electrons that will reach here, that is somewhat considerable. So 1.5 into 10 to the power 10. So at room's temperature it can conduct the current. So this is with respect to mathematics we have proven. In an interview if they are asking this question, then you can prove it like this. So I will use the Boltzmann statistics. Using the Boltzmann statistics, this is the thing that I can write down, that finding the probability, what will be the probability of finding an electron at conduction band, or I should not say conduction band, at the EC energy state, at the EC energy state. What is EC? EC is the lowest energy of the conduction band. So this is the probability, and now there are a lot of states. Number of states are roughly around 2.8 into 10 to the power 19 centimeter cube inverse. So sir, this will be the intrinsic carrier concentration present in our intrinsic semiconductor. So these number of electrons are present in the conduction band. That means these number of holes will be present in the valence band, right? If these many electrons are present in the conduction band, then these many holes will be present in the valence band, because electron hole pair will be generated. But let's understand it with respect to the crystal. So in crystal, what will happen? Like you will be having silicon, and silicon will be having bound electrons. Then again silicon, bound electrons. Now this energy that you are saying, which is 0.0259 electron volt. So this is not a certain number. Like it's not that, sir, there is some electron. This electron will be getting 26 millivolt. So this electron will also get a 26 millivolt. This electron will also get 26 millivolt. This electron volt is also getting 26 millivolt. It's not like that. It is distributive in nature. Have you studied Gaussian distribution, linear distribution in our communication system or in our mathematics? That it is like it is distributed. At some point you can get more energy, and at some point you can get less energy. So basically this 26 milli electron volt packets you are having, some will get more packets, some will get lesser packet. So some electrons may get more energy and some electrons may get lesser energy. And there are silicon atom as well. So basically atom and electron both will be vibrating because of the thermal energy. Some electrons will be vibrating more, some atoms will be vibrating more, and some atoms will be vibrating less. So these atoms will frame a wave-like nature. These atoms will frame a wave-like nature. Basically what I am saying is that, let's just say this atom is going up, this atom is going down, next atom is going up, next atom is going down. So this wave-like nature they have framed, no? Right? And this wave-like nature only is known as phonon. So because of this wave-like nature, if electrons are colliding with this nature, if electrons are colliding with this oscillating atoms, so let's just say there is very high oscillation. Some atoms are having very high oscillation, some atoms are having very lesser oscillation, and electrons are bound to it. If electrons bound to these oscillations, if these bound electrons are colliding with these oscillations, then they can release very high energy, and that energy would be more than enough for them to make a transition from valence band to conduction band. So this is what is written. When an electron is interacting with one of these rare high energy vibrations, then it can gain enough energy in a single event to cross the band gap. So basically electrons are bound, and these atoms are vibrating like this. Some will be vibrating with very high energy, some will be vibrating with lesser energy. So now that energy would be more than enough to break a covalent bond, and electron will be getting enough energy to make a transition from valence band to conduction band. So either you explain by mathematics or you tell them this thing. Okay. So a very good interview question. In some of the other video as well, like some of the educator was also explaining this particular doubt of some student, and he was saying that some trap energy level will be present. Like between the conduction band and valence band, there will be some trap energy level will be present. So these electrons first they will gain 26 millivolt, then they will again gain 26 millivolt. In that manner they will reach to conduction band. He explained that, and in the end he said that don't ask these questions to other educators because they will not be able to explain, like arrogantly, like those people will not know. I am explaining it, but other people will not be able to explain. I am not taking the name of educator, because when I am teaching, I watch the lectures of every educator, every GATE educator, every NPTEL lecture also I watch, and books also I read, just to know that what they are teaching, because I need to teach better than them. That's the bottom line. Okay, this is how you teach, this is how you make your content. So sometimes it is funny that these kind of good questions are answered in this manner, that too arrogantly. Like if you don't know, you can simply say, right? But you answer and then you say that if you ask other teachers, they will not be able to tell. Yeah, they will not be able to tell this explanation. I'm pretty sure he wouldn't even know what is the meaning of trap energy level. Pretty sure. Okay. Yeah. Funny. Sometimes it is funny. And those are actually very famous. Like they have been teaching for 10 to 15 years. They are doing this kind of error. I am teaching for 2 years. Probably I will not teach for 10 years. And if I teach for 10 years, then I will not have any arrogance. Because if I teach only 1 or 2 subjects for 10 years, what kind of arrogance I should have? Why I should have an arrogance for a subject? You are watching this video, no? Like if you teach a particular subject or 2 subjects or 3 subjects for 10 years, you will be master in that. you will be able to teach in good manner. Like you might be a very average guy, then also you will be able to teach it in a very good manner, because 10 years we are reading the same thing. Those only 200 hours you need to teach. Those 200 hours only you need to think. They will be saying I can teach for 1000 hours, I know this thing that thing. गेट के एग्जाम के सवाल सही से होते नहीं, ठीक है, गेट के एग्जाम में थोड़ा सवाल इधर उधर हो दिक्कत हो जाती है. चलो लेट्स नॉट वेस्ट द टाइम. ओके, look, I'm not saying against them. They say against me, that's why I have to say against them. I will never ever start, because when I started this channel, you go to my older videos, you would see how respectfully I used to take the name of educators. Like, he is a very good educator, he has taught this thing, you can study from him. So this is how I used to take their name. But if someone is doing good and you cannot accept it, you always pull their leg, then I'm not there that I will stay silent and just bear everything just for the name of that they are the teachers. I'm also educator, no? Like, no one here is teacher, all are educators, all are doing their work. Teacher is a separate thing. Teacher you can get in your school life. In this coaching life, you will never get the teachers, you will get the educators. Although I try to connect with the students, but again, like, I never ever say anything, any student to get emotionally attached to anything. Like, after the age of 21, you should never get emotionally attached to anything, okay? Not just the educator, to opposite gender as well, to anyone. Never ever try to get emotionally attached, okay? Just few life lesson I am giving. So saying that we think for students, we think that for student, we are there for the students, हम students के लिए अच्छा करना चाहते हैं, हम ऐसे हैं, गुरु भगवान का रूप होता है, ये होता है, वो होता है. And then your language, then see your language. Contradict, कितना contradict. I will tell you one thing, like, in your life, whenever you go, okay, wherever you go, if someone is saying that he is honest, if someone is saying that he is the most genuine person, then he is the biggest fraud, okay? The genuine and the honest person never needs to tell that he is honest or he is genuine. If someone is saying that मैं साहूकार हूँ, मैं सब कुछ, मैं तुम्हारा अच्छा चाहता हूँ, तो उससे खराब कोई नहीं चाहता तुम्हारा. या फिर इधर ही डजंट केयर, या फिर वो आपका खराब चाहता है. वो वास्तव में अच्छा तो नहीं चाहता, क्योंकि जो आपका अच्छा चाहता है ना, उसको बोलने की जरूरत नहीं है. कभी आपने देखा आपका बेस्ट फ्रेंड आपको ये कहता है कि मैं तेरा बेस्ट फ्रेंड हूँ? दो लोग बेस्ट फ्रेंड होते हैं, उन्होंने कभी शेयर ही नहीं किया कि वो बेस्ट फ्रेंड है. उन्होंने आपस में कभी शेयर ही नहीं की ये चीज, है ना? Like, two people who are the best friends, they never say that we are the best friend, right? So those who actually care for you, they will never say it. Parents कभी कहते हैं, like, do your father ever say that he cares for you? No, he just shows the care. He never tells this, right? In our field, you will see a lot of educators saying that we care for you. No, if you care, then why were your course prices were 50K? Why don't you provide courses on YouTube if you care so much? I'm not saying that I care for you. If I care for you, then I will provide every single thing, every single subject, everything on YouTube for free. I cannot do that, right? Because I need to earn as well. I care about myself as well. So if I need to care about my student community, then I need to stop caring about myself, which I cannot do as of now. Who knows, at the age of 30, I might be doing this thing, that I am caring only for the students, not for myself. Because at the 30, who knows at what level I am, right? But as of now, I am 24 and I need to care about myself, right? You are also 21, 22. You also need to care about yourself. Why you are studying? You are studying for the money. So let's be just straightforward. Let's not sugarcoat the things. Let's not do the strawberry talks here, right? So strawberry talks are good to listen. It would make my image better in your eyes, that he is a great educator. What a human being he is. But I am that kind of guy who has always been genuine. Okay, again, now I am saying that I am genuine, but you guys would also know if you are following me for other courses as well. Like, if you are just watching EDC, then you would know it. But if you are following me for the other courses, like, whenever I say anything, I am pretty straightforward for that. If I will be doing this thing, like, if I am saying that basic semiconductor physics will come on YouTube, then it will come on YouTube. If I am saying that complete EDC cannot come on YouTube, then it cannot come on YouTube. That's it. I will never start saying that this subject will be completed and in between I am leaving it. No, this will never happen. Okay, so just being straightforward. Let's get started. Let's go to the next one. Since it is the last lecture, that's why I'm here killing the time. Okay, yeah, Quasi-Fermi level. What we need to study about Quasi-Fermi level. So we don't know, sir, what is this Quasi-Fermi level. Let's solve a question. With respect to the question, you will be able to understand what I mean by Quasi-Fermi level. So there is an n-type semiconductor with equilibrium electron concentration as this and intrinsic carrier concentration as this. Now what you are doing, you are throwing a light. You are doing illumination. Whatever you want to do, you are disturbing the equilibrium. So you have disturbed the equilibrium. Because of that, excess electron hole pair are being generated, which are 10 to the power 13 centimeter cube inverse. So first you need to find out the Fermi level for the first case. Then you need to find out the Fermi level for the second case. Like first case, when it was under equilibrium. When equilibrium was there. So what was the scenario? N naught was 10 to the power 15. Ni was 10 to the power 10. And your P naught would be 10 to the power 5. Right? Do you agree to this point? N naught into P naught is equal to Ni square, because thermal equilibrium is there. I have applied which law? I have applied the mass action law. Right? So what I need to find? First I will find out the position of Fermi energy level in equilibrium. Position of Fermi energy level. So let's find out the position of Fermi energy level. So what do I know? N is equals to Nc e to the power minus Ec minus Ef by kT. Can't apply this formula because I don't know the value of Nc. Then I know that for intrinsic semiconductor, when it was intrinsic, at that time number of states was same, e to the power Ec minus, in place of Ef, what I can put? EFI divided by kT. And when I am doing for n type, I can put EFN here. So from here I can get the answer, right? So n by Ni, what that would be equals to, and this formula also we already know. What we will get? EFN minus EFI would be equals to kT ln n by Ni, right? So kT value I know, it is all happening at room temperature, 10 to the power 15 n naught divided by Ni. So 10 to the power 5 so 0.3 electron volt below. So what do you see here? This is your conduction band. Forget about the valence band. Okay, let's make the valence band as well. And this will be my Fermi energy level. This is my Fermi energy level. This is the conduction band and this is the valence band. What is this gap? 0.3 electron volt, right? Now I can find out this gap. Basically, I can find out the gap using another formula as well. Sorry, not this gap. Really sorry guys. Which gap we have find out? EFN minus EFI we have found out. Sorry. This gap we have find out. This gap is 0.3 electron volt. Now some other formula also I have. Which formula? Sir, here you are using the formula of only electrons, but you can use the formula of holes as well. What will be the number of holes? Number of holes in your n-type semiconductor. What it is? It is an n-type semiconductor. So number of holes in n-type semiconductor. What that would be? Nv e to the power minus Ef minus Ev by kT. And it is going as n-type semiconductor only. So I am putting EFN here, right? And what I will get? Ni is equals to Nv e to the power minus EFI minus Ev by kT. This will be your Ni. Intrinsic carrier concentration. Are you able to understand this point? This formula I am applying only for n-type only. In n-type, will there be holes? Yes, there will be holes. What will be the probability of finding the holes in the valence band? This will be the probability of finding the holes in the valence band. Since you are doing the calculation for n-type, I am putting n here. What will be the number of states in the valence band? Nv. Now, when it was intrinsic, then what was the probability of finding the holes in the valence band? This was the probability of finding the holes in the valence band. What was the density of states? Nv. So Ni was equals to Nv into this thing, right? So if you do this calculation P naught by Ni, what answer you will be getting? So you will be seeing that it would be equals to EFI minus EFN. Okay, that would be equals to, this is your EFI. No, If you multiply both of them, P divided by N naught you will be getting here, EFI would go upward, EFN would be here. So EFI minus EFN, what you are getting? EFI P naught divided by Ni. P naught divided by Ni. So let's do Ni divided by P naught. What I am doing? Ni divided by P naught I am doing. Ni divided by P naught. So what will happen? NV will get cancelled out. This will be upward. This will be plus EV and this will also be plus EV. So that will be cancelled out. This will be minus EFI and this will be plus EFN because that would be coming upward. So you can do the calculation, you will get to know that this is something we are getting. And what we are getting? EFN minus EFI is equals to KT ln Ni by P naught. And it is pretty obvious as well, no? Because you can apply the mass action law here. What is this? KT ln. Here, what I can see is that in place of N naught into P naught, what I could have put? I know that there is a mass action law Ni square. So in place of N naught, I could have put that N naught is equals to Ni square by P naught. So in place of N naught, I could have put Ni square by P naught. So if I put this here, what I will get? Ni by P naught. The same formula I am getting here. Basically, if you solve this, the same answer you will get, which is 0.3 electron volt. And it is pretty obvious as well, no? Because we have seen that for N-type semiconductor, if I draw the energy band diagrams, then conduction band, valence band, intrinsic Fermi level, and your Fermi level will be near to your conduction band. Okay, and the gap between intrinsic Fermi level and EFN is 0.3 electron volt. This we have already seen, and it is pretty obvious as well because here there is mass action law valid. So in place of N naught, you can put Ni square by P naught. So in place of N naught, if I put Ni square by P naught, so what I am getting? The same thing I am getting, this same formula I am getting. So answer would also be same. Simply you put the value of Ni, what that would be? 10 to the power 10. What will be the value of P naught? 10 to the power 5. So what you will get here? ln 10 to the power 5. Here also I am getting ln 10 to the power 5. KT value will be 0.026. So here the same answer you will be getting 0.3 electron volt. So there is only one Fermi level which is near to the conduction band, and the gap between the intrinsic Fermi level and the Fermi level of N-type is 0.3 electron volt. Till this is the condition of equilibrium. Till this point everything is fine. Now what we are doing is that we are disturbing the equilibrium. So number of electrons, what will be the number of electrons? 10 to the power 15 plus 10 to the power 13. So now the number of electrons have reached to 10 to the power 13 plus 10 to the power 15. So you can write it down as 101 or 1.01 10 to the power 15. So this will be 100 into 10 to the power 13. That would be 101 into 10 to the power 13 and 1.01 into 10 to the power 15. So there is not a significant change in the number of electrons. But what will be the number of holes? P naught plus delta P, 10 to the power 5 plus, previously it was 10 to the power 5, now plus 10 to the power 13. So it will be nearly equals to 10 to the power 13. Now if I apply the formula that EFI, now what is the scenario? Equilibrium is disturbed. Equilibrium is disturbed. This is the scenario of non-equilibrium. Now I am not deriving the formula, I already know. EFN minus EFI. EFN minus EFI is given as KT ln n number of electrons divided by Ni. So number of electrons are n this time divided by Ni. So almost the same answer you will be getting. Value of n is 1.01 10 to the power 15 divided by 10 to the power 13. So previously actually I was getting the answer as 0.299. So I will write down the exact answer 0.299. Okay, here the answer was 0.299 electron volt. So let's write down the exact answer. Just I know that some answer would be changing, like a bit of answer would be changing, because 1.01 Ni value is 10 to the power 10, sorry, 10 to the power 10, right? Ni value is 10 to the power 10. So 1.01 into 10 to the power 5, and then you need to take ln, then 0.0259. ये कम कैसे आ रहा है भाई पहले से? 0.0259 1.015 10 to the power 5 01 ln into 0.026. Yeah, nearly the same only we are getting. In the next page I have written it down, 0.2982, 0.2984. So here it will come out to be 0.2982. Okay, 0.2982, 0.2982, and now it is coming out to be 0.2984. That means there is no significant change. But if you apply the other formula, of EFN minus EFI, what was the other formula? KT ln Ni by P. What do you get? 0.026 ln, what is the value of Ni? 10 to the power 10 divided by what is the value of P? 10 to the power 13. So if you solve it, what you are getting? 10 to the power 3, right? Then you take ln into 0.026, 0.179, but in the negative. What does that mean? That means EI minus EFN, you are getting 0.179. Here you are saying that EFN minus EFI is this value, and now you are saying that it is this value. There is a problem, right? So now you need to define two levels. When there was equilibrium, from this formula and from this formula you are getting the same answer, because mass action law is valid. But here mass action law is not valid. Number of electrons multiply with number of holes. 10 to the power 28. It is not equal to Ni square. Ni square is 10 to the power 20 only. So when this is the scenario, when mass action law is not valid, when you are not under the equilibrium, then you need to define two levels. This is n-type semiconductor only, but in n-type semiconductor as well, I will define two levels, that will be FNQ and FPQ. So actually here I should write FNQ, and here what I will write FPQ. So with respect to the hole concentration and with respect to the electron concentration, I am getting different answers. So these are your imaginary two quasi-Fermi levels. Are you able to understand this point or not? So before equilibrium, this was the scenario. So here I can say that my EFN was equals to EFP. If I am calculating the difference taking the whole concentration into action, or if I am calculating the difference taking the electron concentration into action, I was getting the same difference, that was 0.2982. Then mass action law became invalid, non-equilibrium condition. So you get to know that here number of electrons are not getting changed. Then if you are finding the gap taking number of electrons only, you are getting the same gap, 0.2984, just nearly the same gap. But if you are finding the gap using whole concentration, then your answer is 0.179 electron volt. What does that mean? This Fermi level is below intrinsic Fermi level by 0.179 electron volt. So basically what you are seeing is that this EFN is being divided into two parts. This EFN is being divided into two parts. Those two parts are EFNQ and EFPQ. Okay. So this theory has been written. In equilibrium, a semiconductor has only one Fermi level. This describes both electron and holes. But in non-equilibrium, electrons and hole cannot be described by the same Fermi level. Electrons will have their own Fermi level. Holes will have their own Fermi level. Electrons will have their own Fermi level, that is known as electron quasi-Fermi level, and holes will have their own Fermi level, that is known as hole quasi-Fermi level. Okay. So what is the key idea? Key idea is that if you are at the equilibrium, then EFN would be equals to EFP would be equals to EF. So you can simply call it EF. But if there is extra charge carriers present, then EFN and EFP will be split apart. These will be split apart. Okay. And as much gap is there, if this gap is larger, that means there is more unequilibrium. What does that mean? That means you are more towards non-equilibrium. Basically, when this gap was 0, when EFN minus EFP was 0, when this gap was 0, here EFN was equal to EFP. When this gap was 0, that means equilibrium, right? Equilibrium. equilibrium. Yeah. When this gap was 0, that means there was equilibrium. When this gap has become 0.2984 plus 0.19179 electron volt, then the equilibrium is disturbed. So looking at the diagram, if you see that you are getting 2 Fermi level, that means the concept of quasi-Fermi level has come into action. What does that mean? That means there is non-equilibrium condition in your semiconductor. Sir, why this non-equilibrium condition is important? Because we are going to use this concept in PN junction. So where it will be used, that you are not able to understand. But sir, what is the meaning of quasi-Fermi level, that you are able to understand. Where this meaning will be used, that we will see in PN junction. But as of now, what you have understood, that ideally we should have only one Fermi level if equilibrium condition is there. In non-equilibrium condition, we will get 2 Fermi level. If excess carriers are there, if excess carriers are generated, then we will get 2 Fermi level in same semiconductor, in one semiconductor only. Okay, all good. So that's it. This is the meaning of quasi-Fermi level. There is very rare chance that any question can be asked from here, but it will be used in our analysis in PN junction. That's why we are studying it here. All good, all fine. With the example it is clear to you, otherwise it would become very complex to understand, but with the example it is clear. Number of electrons, number of holes, thermal equilibrium, this was the condition. Thermal equilibrium disturbed, this is the condition. That means one Fermi level is split into 2 Fermi levels. These are known as quasi-Fermi level, one for electron, one for holes. As much gap is there, as much you are moving towards a non-equilibrium condition. That means the larger the separation between them, the stronger the non-equilibrium condition. Okay, let's see this question. The equilibrium and steady state before and after illumination of a semiconductor are represented by the energy band diagram shown below. These two energy band diagram they have made at 300 Kelvin. Intrinsic carrier concentration they have given, mobility and all these things they have given, electron charge they have given, KT value they have given. Calculate the percentage increment in the conductivity due to illumination. So this is before and this is after. So what was the condition before? What is the condition after? That we need to see. So what we need to find? So first we are solving for the before illumination. Before illumination. So what would be the conductivity? Conductivity would be N Q mu N plus P Q mu P. So our target is to find N and P. What do I know? EFN minus EFI. EFN minus EFI. That would be equals to KT ln N by Ni. This is the formula. EFN minus EFI. KT ln N by Ni. From here in this manner you can derive it, KT ln N by Ni. But this is before equilibrium, so I will write down N naught by Ni. This is at the equilibrium, no? So N naught by Ni I am writing down. So this value is 0.3 electron volt. It is equals to 0.0259 electron volt. N naught by Ni. Ni value is 10 to the power 10. So previous value you will be getting the previous values only. So yeah, 10 to the power 10. You will be getting 10 to the power 15 here. Roughly around 10 to the power 15 you will be getting. So let's check it. Still we will check it. 0.3 divided by 0.0259. Then e to the power 1.07 into 10 to the power 5. And then 10 to the power 10. Yeah. So N naught value you are eventually getting, because Ni value we already know. That is 10 to the power 10. Ni value is 10 to the power 10. That would be 1.07 10 to the power 15 centimeter cube inverse. So this was your N naught value. What will be the value of P naught? P naught will be somewhat around 10 to the power 5. So nearly you can ignore it. 10 to the power 5 will not make much of the conductivity, right? You can ignore it. So sigma will be equals to 1.07 into 10 to the power 15 into 1.6 into 10 power minus 19 into mu n. What is the value of mu n? 1350. So let's see what answer you will be getting. 1.07 into 1.6 into 0.135. 1.07 into 1.6 into 0.1350. So 0.23 सीमेन per centimeter. Say yes or no. Okay, because everything is going into the centimeter, rest all the things are fine. Now after illumination you can see that this value they did not mention, but this value they have mentioned. EFN minus EFP, EFI minus EFPQ they have mentioned. EFI minus EFPQ they have mentioned. So here I have seen the formula. EFPQ minus EFI was KT ln Ni by P. So EFI minus EFPQ would be KT ln P by Ni. Right? So what I need to do now after illumination. After illumination, what they are saying is that your EFI minus EFPQ is given by KT ln P by Ni. 0.026 is equals to 0.3 again ln P by Ni. Same calculation, no? 0.3, 0.025. This gap is 0.3, this gap is 0.3. So from here, what do you understand? That P value is coming out to be, after illumination, P value is coming out to be 10 to the power 15 or 1.07, whatever you want to write down, 1.07 into 10 to the power 15 centimeter cube inverse. Now this P value would have been what? This P value would have been P naught plus excess carrier. So what is this P value? 1.07 into 10 to the power 15. What was your P naught value? 10 to the power 5. That means all of these is converted into the excess carrier only, right? So from here you can see that delta P is approximately equals to 1.07 into 10 to the power 15 only. So after the illumination, whatever the number of holes you are getting, you get to know that these number of holes are much higher than the carrier, much higher than thermal equilibrium, or you can say before illumination condition. So these are much higher than the thermal equilibrium number of holes. So these holes are much higher. That means all these holes are generated because of illumination only. So same number of electrons will also be generated. A lot of people will forget this thing. They will forget to write down that number of electrons will also be generated in the same amount. No. So same number of electrons will also be generated. So now what is the condition? That this is the number of electrons. So this is the number of holes. But what is the number of electron now? The thermal equilibrium electron plus the excess electron. So what is the thermal equilibrium electron? Thermal equilibrium electrons were 1.07 into 10 to the power 15 and excess are also 1.07 into 10 to the power 15. So what it would be? 1.07 into 10 to the power 15 plus excess 1.07 into 10 to the power 15. So it would be 2.14 into 10 to the power 15 centimeter cube inverse. So these are the number of electrons and these are the number of holes, right? Although this calculation was, this calculation was also necessary to find out the delta P. From delta P I can find out the delta N. Now I have the value of delta N, I have the value of P as well. Now my job will be done, because now what will be my sigma? Sigma nu. Here I am putting sigma old. So my sigma nu will be this N, which is 2.14 into 10 to the power 15 and Q mu. What is the value of mu? 1350 plus, what is the value of P? This is the value of P. P Q. What is the value of Q? 1.6 into 10 power minus 19. What is the value of mu? Mu value is 460. 460. So what will be this calculation? This calculation will simply be double of this. That means it will be 0.46 plus, what will be this calculation? This will be 0.23 into 460 divided by 0.23 into 460 divided by 1350. So you can do the calculation on your own. 0.078. This is coming out to be 0.078. Isn't it too much? Yeah, plus 0.046, sorry, 0.46, 0.53, 0.5387. This is your sigma nu. So what is the percentage change? Let's just say I was having 50 rupees. Now I am having 120 rupees. Or you can say now I am having 100 rupees. So how will I find out the percentage change? 100 minus 50 divided by 50. Basically from 50 to 100 you have. That means you have got the 100% growth, no? From 60 to 60 you get. What does that mean? That means 20% of this growth. In 50 you get plus 20%. So how will you find out? 60 minus 50 divided by 50 into 100, right? So 100 minus 50 divided by 50. That means new minus old divided by old. So what they are asking? Percentage increment. Percentage increment. That would be new minus old divided by old. Into 100%. So 134% you are getting. Okay, well and good. Understood? Yeah, so that's it about this question. I hope you are able to understand. So whenever the question is coming on conductivity, always remember that you need to take care of minority excess carrier concentration and majority excess carrier concentration as well, because a lot of time people will be forgetting this. They will forget this delta n, and if you forget this delta n, answer will be messed up, because here it will be twice of that. So this delta n you should not be forgetting. Okay, now we will discuss 6 questions, easy questions these are. This is the first one, this is the second one, third, fourth, fifth, and then this is sixth. So these 6 questions you try on your own. I think you should be able to solve most of the questions on your own. Out of 6, at least 4 you should be able to solve. Out of 6, 4 you should be able to solve. Okay, so let me take a break and then I will come back and we will start solving these questions, and then our basic semiconductor physics will be completed. Okay, yeah, so did you try this question? In this question, what you need to find out? Electron current density you need to find out. So there is a semiconductor. Okay, they are talking about only electrons, so surely it is an n-type semiconductor, but let's not, it is not important whether it is n-type or p-type, whatever it is. And you can see the doping profile. Here there is lesser doping. At x equals to 0 there is lesser doping, and at x equals to L there will be more doping, and you can directly see here as well. 10 to the power 15 q alpha x divided by kt. That means at x equals to 0 you will be getting the value of 10 to the power 15, and then at x equals to infinity you will be getting infinite value. That means it will be increasing. Here there is no negative sign. If it was negative sign, then it would be decreasing, but your coefficient is positive only, so that's why it is increasing. So value is exponentially increasing. So electron concentration, here there is lesser, but here there is more. If here there is more concentration, then what will happen? Electrons will diffuse in this direction, and because of that, this will be the direction of diffusion current. Okay, so this is the direction of your diffusion current. Now you let me know in which direction electric field has been applied. In the direction of electric field, the slope of conduction band will be positive. In the direction of electric field, the slope of conduction band will be positive. So this is the direction of electric field. Now it is external electric field or it is built-in electric field, that we don't know. But one thing I know. What do I know? I know that my electric field is in this direction. That's the only thing I know. I am not pretty sure that whether it is built-in or total. Sorry, this is the total electric field. Whether it is coming because of the external is being added or it is opposed, I don't know anything. But I just know that total electric field is in this direction. Total electric field is in this direction. That I know. Okay, so that Electric field value also I know. What is the value of this electric field? So slope, if you are already having, what you are having? You are having the slope of this dEC by dx you are having. That is given by minus 0.1 electron volt per centimeter. Just by looking at the unit you can tell electron volt per centimeter. I just need to take care of electron. So if that is gone, my electric field will be 0.1 volt per centimeter. Direction here I have shown. If this is the direction of electric field, then what will happen? Where the electrons will diffuse, where the electrons will drift in this direction. So where will be the drift current? So this will be the direction of your drift current. So this will be your I drift. So you can see that I diffusion and I drift both are opposing each other, right? Diffusion current and drift current are opposing each other. So you need to find out the diffusion current and you need to find out the drift current. After that you will be able to know that what will be the value of current density at x equals to 0. Okay. So let's find out the current density they are talking about. So let's first find out the diffusion current. What will be the diffusion current? So diffusion current would be Q dnx by dx. So 1.6 into 10 to the power minus 19. So always we should prefer making the diagram. If you make the diagram, your job is done. That's it. Okay. So 1.6 into 10 to the power minus 19. What is the value of dn? 36. Everything is going in centimeter square. And now dnx by dx. So what it would be? So what is your nx? Nx is 10 to the power 15 alpha x by kt. Your nx is 10 to the power 15 e to the power alpha. What is the value of alpha? Alpha is 0.1 x by kt. What will be the value of kt by q? That will be 0.026 volt, no? So directly I am putting here 0.026. This I think I can do, right? What will be the differentiation of this particular thing? 10 to the power 15 will be constant. A to the power 0.1 x divided by 0.026 into 0.1 divided by 0.026. You need to find out that diffusion current at x equals to 0. Okay, so let's see. 1.6 into 36 into 0.1 divided by 0.026. Now 0.1 volt was there and this was also volt only. Volt per centimeter. Yeah, everything is going fine. Ampere per centimeter square. So 2 to 1 I am getting. So 10 to the power minus 4 is there. So 0.22, no? 0.22 you can say. Yeah, 2.22. Basically this is what you are getting. 2.21 into 10 to the power minus 2 ampere per centimeter square. When you solve it, this is what you will get. At x equals to 0, because x equals to 0 I have put here. So this is what you are getting. Okay. This is your diffusion current at x equals to 0. What is your drift current? So drift current would be n x q mu e, right? Value of mu is given? No, it is not given. We can find it out. How we will find out? D is equals to uv. So mu into vt, mu n. So mu n will be equals to dn by vt. What is the value of dn? Dn is 36. Vt is 0.026. 36 divided by 0.026, right? 36 divided by 0.026. 1384.61. Okay. What is the unit? Vd is equals to mu e. Vd is centimeter square volt into second, right? So let's solve it. Now you need to find it out at x equals to 0. So nx value at x equals to 0, what that would be? value of nx at x equals to 0, 10 to the power 15, because if you put x equals to 0 here, e to the power 0 will be 1. So 10 to the power 15. What is the value of q? 1.6 into 10 power minus 19. What is the value of mu n? That is 36 upon 0.026 into what is the value of e? What is the value of e? Value of e is 0.1. So isn't it the same calculation? 0.1, 0.1, 0.026, 0.026, 36, 36, 10 to the power 15, 10 to the power 15, 1.6 into 10 to the power minus 19, 1.6 into 10 to the power minus 19. So what answer you will be getting? 2.21 into 10 to the power minus 2 ampere per centimeter square. Will you add them up? No. Why so? Because you know that what is your total current? Total current is both are in the opposite direction. So both are having the same magnitude, both are in the opposite direction. What does that mean? 0. What do you understand from that? That means there is no applied battery, because if there was battery, current would have surely flown. If I had connected a battery, current would have surely flown. So there was no battery actually. So what was the value? How would I make the EFN? This is how I would have made the EFN. This would have been your EFN with 0 slope. EFN would be near to, here it would be nearer, and after that it would be further. So this would have been your EFN. Right. Here there is more doping, after that there is lesser doping. Is that clear to you or not? Okay, very simple question. Just to make the diagram, write down the diffusion current, write down the drift current, and your job is done. Okay, well and good. Here, how would I get the electric field? From here I would get the electric field. That is also clear to you. Because what is the formula of electric field? 1 by q dEc by dx. So from there I get this expression. This question, this is a good question only. So consider a uniformly doped n-type semiconductor. DC voltage as shown, ND value is given, Ni value is given. Okay, ND value is given, Ni value is given. ND is 10 to the power 16 centimeter cube inverse. Ni value is given as 10 to the power 10 centimeter cube inverse. Vt value is also given, 26 millivolt. Now you know that what kind of diagram you will be getting. Can you draw the diagram? Yes sir. What is the direction of electric field? Sir, here there is positive potential, here there is zero potential, so I can say negative potential, and it is uniformly doped, so only electric field will be this. This is your total electric field. So this is the electric field. So what kind of diagram you will be getting? So this kind of diagram you will be getting. And surely what will be the direction of current? From the positive. Do you understand the meaning of this 1 volt? This 1 volt means this is the 1 volt battery. If this is grounded, so 0 and this point will be 1 volt. So this is how I can show it, 1 volt. Okay, and then there is semiconductor, and then there is ground. So ground can be attached. So now this is the structure, and this structure we have already seen, right? I hope you know the meaning of this 1 volt. In network analysis, a lot of time we do this thing. In analog electronics as well, we do this thing, right? So conduction band and valence band. And then there, in between there is Fermi energy level. It is an n-type semiconductor, so intrinsic Fermi energy level. So if it is an n-type semiconductor uniformly doped, what does that mean? In this direction there is a current, so here I will get a EFN as well, right? Now what they are saying, this is your x equals to 0. So here whatever the value you are getting, that is known as EC0, and here what you are getting, that is known as EC1. EFI is of no use for us. EFI is of no use. Or let's see if it is of any use or not. Now in EF, what they are saying, EF is equals to EF1 here and EF0 here. You need to find out the value of EF0 minus EC1. What you need to find out? EF0 minus EC1. This you need to find out. EF0 minus EC1. So my target is to find out EF0 minus EC1. Now ND and Ni I am having. ND and Ni I am having. Then I could see that surely this value I can find out. Because if this is ND, this is Ni, then I can surely tell that number of electrons will be 10 to the power 16 only. So I am having the number of electrons, I am having the intrinsic carrier concentration. So this distance I can find out. And one more thing, energy gap is 1.1 electron volt. What does that mean? That means, shall I make the diagram again? Let's make the diagram again here in a bigger manner. EC naught, EC1, EF1, EF naught, EFI. And I know that what will be the difference between this guy and this guy? Like this total distance. This total distance will be 1.1 electron volt. Electron volt. What will be the distance between these two? Like distance are parallel. Everywhere distance are parallel. So what will be this distance? That I can find out. EF1 minus EFI, or you can say this distance also I can find out. EF naught minus this distance, whatever it is. So basically this distance I am finding out. So what I am doing? EFN minus EFI, that would be equals to KT ln n by Ni. KT is 0.026 ln n by Ni. What is the value of n? 10 to the power 16 divided by 10 to the power 10. So 10 to the power 6 ln into 0.026. So 0.359, or I can write it down as 0.36. So this value is coming out to be 0.36 electron volt. Can you let me know what will be the distance between these two guys? So total is 1.1 electron volt, and by default I will say that, by default what I will say? By default I will say that this intrinsic Fermi level will be right in between, right in the middle. So what will be this distance? This distance is going to be 0.55 electron volt. And if I know this distance, then I can tell this distance as well. What I can tell? This distance I can tell. What is this distance? EC1 minus EFN. What that would be? Total is 1.1. So 1.1 minus 0.05 minus 0.36. So 1.1 minus 0.36 minus 0.55. So 0.19. Are you able to understand this point? So what I have found out? 0.19. And all these are electron volt. So what I have found out? EC1 minus EFN. Because all these points are parallel, no? EC1, EFN is parallel. So I have found out EC1 minus EF1. That is equals to 0.1 electron volt. What is my target? I will look at the target. Target is EF naught minus EC1. Target is EF naught minus EC1. This is the target. So I need the EC1, but I don't need the EF naught, EF1. So basically I need some relation between EF1 and EF naught. Basically in the answer I need EC1, and then in the answer I need EF naught, but I don't need EF1. So if I get a relation between EF1 and EF naught, my job will be done, right? So what I will try to do is that I will try to find out the distance between EF1 and EF naught, right? EF naught minus EC1 you need, no? EF1 minus EC naught, if you can find out the distance between EC naught minus ES1, EC naught minus EF1, just a second. Yeah, so what I was saying that I need to find out the relation between EF naught and EF1. I need to find out the relation between EF naught and EF1. This would be my target. Now what do I know? What do I see here? That my applied electric field is 1 volt per centimeter. Do you agree to this point? 1 volt is applied towards 1 centimeter. So my applied electric field is 1 volt per centimeter. And I know that if this is the applied electric field, then what will be my 1 by q equals to d EC by dx. So slope in my conduction band would be equals to slope in my conduction band dEC by dx. That would be equals to 1 electron volt per centimeter. But sir, you need to find out the relation between EF naught and EF1. No, with the slope you can find out the relation between EC naught and EC1. What I am saying is that, sir, with the slope you can find out the relation between EC naught and EC1, but you need to find out the relation between EF naught and EF1. So just let me know one thing, whatever the difference between EC naught and EC1, whatever the difference between EC naught and EC1 you will get. Basically what I mean to say is that whatever this slope is, it will have the same slope, no? Are you able to understand this point, what I am saying? Whatever the distance is there between these 2 points, the same distance will be there between these 2 points as well. Are you able to understand this point? When I was reaching here, EC1 minus EF1, I got to know that in the final answer I need EF naught and I don't need EF1. That means EF naught and EF1 is my target. This distance is my target. Now I got to know that what is the information given. With the information given, I can see that I can find out the slope in the conduction band. I am able to find out the slope in the conduction band. What is that slope? That slope is 1 volt per centimeter. What was this? This end was, everything was happening here at x equals to 0. And what was this end? This end was x equals to 1 centimeter. So this particular distance, this much distance is 1 centimeter. This much distance is 1 centimeter. This is your EC1, this is your EC naught. And I have found out that this slope is 1 electron volt per centimeter. So whatever this value is, I don't know whatever this value is, this EC naught will be plus 1 electron volt. Say yes or no. Basically this EC naught will be equals to EC1 plus EC naught would be equals to EC1 plus 1 electron volt. Say yes or no. Then only you would see that EC naught, if EC naught is equals to EC1 plus 1 electron volt, then only the slope will become 1 electron volt per centimeter, no? Because what is EC naught? EC1 plus 1 electron volt. What will be the slope here? The slope will be EC naught minus EC1 divided by 1 centimeter, because this distance is 1 centimeter, right? So what is the slope? Slope is 1 electron volt per centimeter. This and this get cancelled out. So EC naught is coming out to be 1 electron volt plus EC1. 1 electron volt plus EC1. Basically the slope here is 1 electron volt per centimeter and the distance is 1 centimeter. What does that mean? That means the distance between these two guys, this would have been 1 electron volt. So what you got to know? That my EC naught minus EC1 is equals to 1 electron volt. Since lines are parallel, because it is uniformly doped and everything is there, since lines are parallel, so EF naught minus EF1 is equals to 1 electron volt. Basically everyone got the same slope, no? If everyone got the same slope and everyone is there between 1 centimeter distance, so similar thing is happening. That means EF naught minus EF1 will also be 1 electron volt. So what you are having now? Equation 1 and equation 2. From equation 1 and equation 2, what I need to do? EF naught minus EC1. So from 2 minus 1 I need to do. Equation 2 minus equation 1. So what I am getting? EF naught minus EF1. So that would be 1 minus 0.91, that would be 0.81 electron volt. So this will be your final answer. Did you understand this question or not? So whatever the information was given, just use that information, that's it. Okay? Using the information, we got to know this particular thing. We started from here, that ND, NI value I am having, so this distance I can find out, this distance I find out, this distance also I know, then this distance I can find out. So EC1, EF1, this equation I got. Now I know that I don't need EF1 in my final answer, but I need EF naught in my final answer. So I need the relation between EF naught and EF1. EF naught and EF1 can come from the current, because I know that our current is proportional to the slope of Fermi energy level. but there is no relation of the current, like in the current value nothing is given and I don't even know the exact relation. But what do I know? From here I know that EC0 minus EC1, I can do something here, right? Because I know the electric field value. If I know the electric field value, then I can know that this slope will be 1 electron volt per centimeter. 1 electron volt per centimeter. If I know this slope, that means whatever the value is here, this would be EC1 plus 1 electron volt. So similar thing will happen here. Whatever the value is here, this would be EF1 plus 1 electron volt. So EF0 minus EF1 is coming out to be 1 electron volt. Using this expression, I got this answer. Okay. Solve this question. Energy band diagram with respect to x is given. At equilibrium, you need to draw the potential plot. Electric field is equals to 1 by q dEc by dx, and this electric field is equals to minus dV by dx, minus dVx by dx, and this is also with respect to x. Electric field will also be a function of x only, so that you can understand. But let's draw the. Now only conduction band is made. Why so? Because you know that whatever the structure of conduction band you will see, the same structure you will see in the valence band, same structure you will see in the intrinsic Fermi level as well. That's why they did not draw any other bands. And since it is at equilibrium, then Fermi energy level will have zero slope. So this kind of diagram we did not even see. You did not see, don't care. What you need to do you need to find out any expression or anything like that? No. Only thing is you need to draw the graph. So sir, we used to see the flat band diagrams. These kind of diagrams we used to see. Yes, we will see these kind of diagrams only. But if any other random diagram is coming, we will try to solve. What we need to do, we just need to plot the potential plot. So can we draw the potential plot? Surely we can draw the potential plot. How we will draw? What I can see? Between, I will mark up some points. Between x1 to x2, what is happening? If I need to relate voltage with this particular expression, then what I need to do? If I need to relate voltage and energy, then in between electric field will come. So between x1 to x2, what do you see? The slope is positive. The slope is positive. So this value will be positive. That means electric field will be positive. If electric field is positive, that means dVx by dx will be negative. That means Vx will be decreasing. So till this point, everything was till this point. What was the scenario? Here, this EC was constant. That means electric field was 0. That means Vx was also constant. What I mean to say is that between 0 to x1, EC was constant, right? This EC was constant. That means, sorry, not constant, uniform. If it was uniform, then differentiation was 0. That means electric field was 0. If electric field is 0, that means dVx by dx is 0. That means Vx is uniform. So Vx was uniform. Now your EC is increase. Your EC is increasing, right? Your EC is increasing. That's why dEc by dx will be positive. Here the slope will be positive. No, this is what I am saying. Slope will be positive. Slope is positive. If slope is positive, then what will happen? Electric field will be positive. Then dV by dx will be negative because electric field is equal to minus dV by dx. So dV by dx will be negative. What does that mean? That means Vx will be decreasing, or you can say Vx will be having negative slope as well. Vx will be decreasing, having the negative slope. So this is how it should go between x1 to x2. Say yes or no. Now between x2 to x3, between x2 to x3, what do you see? Slope is negative. Between x2 to x3, the slope is negative, no? dEc by dx, slope is negative, right? If you draw a slope here, negative. We draw a slope here, slope is negative. Positive slope means this is the positive slope. Now here the slope is negative slope. So this slope is negative, that means electric field is negative. If electric field is negative, that means dVx by dx would be positive. So now the slope will be positive. So till x3, the slope will be positive. After x3 what is happening? After x3 the slope is again positive, so this value again positive, that means electric field again positive, that means dvx by dx again negative. What does that mean? Vx is again decreasing, and then after that it becomes constant. So if EC is becoming constant, that means this value, sorry, EC is becoming uniform, then this value will be 0. Electric field is 0, then Vx is also uniform. So there you go. This is the diagram of your Vx. So it's like a mirror image. If you put a mirror here, then what you will get? Like, do you remember? This was our semiconductor, right? With respect to x, what was our potential plot? Here potential is more, here potential is more, here potential is less, right? So what was our potential plot? This was our potential plot. Here potential is more, here potential is less. So this was our potential plot. And how did I make our conduction band diagram? In the direction of electric field, this will be your conduction band diagram. So this was your potential plot, and this was your conduction band diagram plot. So again, it's like that. If you just take the mirror image, this guy goes here, this guy goes here. So if EC diagram is made, if the energy diagram is made and you need to draw the voltage diagram, just take the mirror image. About x-axis, take the mirror image. Okay. Although taking mirror image, all these things are not a really good method. We should go by these methods. Simply write down the expression. Simply write down the expression and see. dcx by dx is positive. dcx by dx is positive. Since it is positive, so dvx by dx will be negative. That means slope will be negative. Okay. All good. Fine. And here also you can see that slope is going towards 0. dc, what I mean to say is that dec by dx value is going towards 0. Whatever the value was here, whatever the value of a slope was here, after that the slope is becoming 0. So slowly dec by dx is going towards 0. That means dvx by dx will also go towards 0 only. You can see that it is going towards 0. You can see that here also it is going towards 0. So one side is, once it has become 0, here also this slope is also becoming 0. Basically what I mean to say is that if the slope in the energy is 0, then the slope in the voltage will also be 0. Okay. This is rising, decaying, rising. So positive slope, dvx by dx, negative slope. Negative slope, positive slope. Positive slope, negative slope. Zero slope, zero slope. Zero slope, zero slope. Right? So what I mean to say is that if EC is having positive slope, then Vx will have negative slope, and vice versa. And vice versa. Okay, there you go. Next, potential plot is given across a n-type semiconductor at thermal equilibrium at T equals to 300 Kelvin is shown. Find the ratio of doping at x equals to 0 and x equals to 6. N-type semiconductor. Under equilibrium, that means there is no external bias. This is your n-type semiconductor. Potential plot is given. Now, where will be higher doping, where will be lesser doping? N-type semiconductor is there. What do you think? If I make higher doping here, then what will happen? Here there will be positive and here there will be negative. So electric field will be built up in this direction. Basically, here there will be positive potential, here there will be negative potential. So potential at x equals to 6 micrometer will be more, and potential at x equals to 0 micrometer will be less. Is it the scenario? No. At 0 micrometer there is more potential, and at 6 micrometer there is lesser potential. That means what is the profile of doping? The profile of doping is like this. Now what will happen? Electrons will diffuse here. So here you will get positive charge and here you will get negative charge. So what will happen? Forget about the direction of electric field. I don't care about the direction of electric field. I just know one thing, that at x equals to 0 there is more potential, and at x equals to 6 there is lesser potential. Right? What is the potential difference? Do you remember this formula? I told you potential difference would be equals to Vt ln ratio of the concentration. Ratio of the concentration. I am just putting n1 by n2. What I need to find? Ratio of the concentration at x equals to 0 divided by ratio of the concentration at x equals to 6. This value will be greater than 1 or less than 1? Greater than 1. Why so? Because concentration at x equals to 0 is more and at x equals to 6 is less. So whatever the answer I will get, I just need to make sure that it is greater than 1. So delta V, what is the potential difference? 30 millivolt divided by what will be the value of Vt? Not given. I will take 26 millivolt. Or let's take 0.0259. ln n1 by n2. Okay. So 0.03 divided by 0.0259 e to the power 3.12. So what it is coming out to be? That is coming out to be 3.12. So if you solve it, n1 by n2 is coming out to be 3.12. Now let's just say this was my answer. This answer came. n1 by n2, this answer came. Okay. And then I know that at 6 there will be more equilibrium. Let's just say in my case at 6 there was more equilibrium and at 0 there was lesser equilibrium. Then what I would have done? I would have just done the reciprocal, because they are asking at x equals to 0 divided by x equals to 6. You know that this answer should be greater than 1, because at x equals to 0 there will be more concentration, at x equals to 6 there will be lesser concentration. You know this formula is also there. Let's just say you applied the formula and you got the answer n1 by n2 as, let's just say 1 upon 3.12. This answer you got. This answer you got. But you know that answer should be greater than 1. That means here whatever that you put, that should be put in the reciprocal. I told you here n1 by n2 you will remember. Sir, what will come upper side, what will come downward side, don't care about that thing. n1 by n2 you will remember. So whatever the answer came, I know that answer should be greater than 1, then I would do the reciprocal. There you go, answer would be 3.12. So in diffusion current, we are very smartly solving the problem, right? Whenever there is a concentration gradient, very smartly we solve the questions. We don't care about the sign. Whether it is current, whatever it is, we never care about the sign. We make the diagram and then we see. Well and good. Okay, so this is the answer. This question. The resistivity at a room temperature is given. At room temperature for intrinsic silicon is given like this. This is the resistivity for intrinsic silicon. Do you remember resistivity? Resistivity is simply the reciprocal of conductivity, right? N-type silicon sample. If it was N-type silicon sample, then this was the resistivity. A bar of silicon having 3 mm long and rectangular cross section area 3 mm long, and cross section area is 5 into 10 to the power 4, sorry, 5 into 10 to the power 3 millimeter square. Okay. Now this is also in millimeter only. Current of 1 microampere is flowing through the bar and the voltage is found to be 50 millivolt. So when you apply a battery of 50 millivolt, here, so in these kind of questions, if you feel like that, sir, a lot of information is given, always make the diagram. Just make the diagram and your job will be done. 50 millivolt battery with the current of 1 microampere. Okay. If the same bar was made of intrinsic silicon, then what would be the voltage across the bar considering the same current flow? Okay, this was N-type. In N-type, this was the scenario. In N-type, what was the scenario? In N-type, the scenario was, if I am applying 50 millivolt, then I am getting 1 microampere current into the resistance, whatever the resistance it provides. What is the formula of resistance? R is equals to rho L by A. Now what you are doing, you are not changing L, you are not changing A. So L and A are constant. You are changing the material. If you are changing the material, then rho will change, no? Only rho will change, right? Here I am talking about intrinsic. For extrinsic, what is the scenario? The current remains the same. Current remains the same. Okay. You need to find out the voltage, and now, sorry, this was for N-type. Really sorry. This scenario was for the N-type. Now you need to find out Ri value. Now you know that length and area you are not changing, that means R is actually proportional to rho here. Although rho is a proportionality constant, that I know, but actually it is coming out to be proportional to rho only because L and A you are not changing. When you are moving from N type to intrinsic, you are not changing L and A. Only thing you are changing is that is rho, right? Fine. Okay. So what I will do is that V divided by 50 millivolt, 1 microampere will be cancelled out. Ri value will be equals to rho I divided by rho n. So rho I is 8.33 into 10 to the power minus rho I is 2 into 10 to the power 3. 2.3 into 10 to the power 3 divided by 8.33 into 10 to the power minus 2. So what is the answer of V you will get? So 2.3 into 50, 2.3 into 50. So milli and 10 to the power 3 will be cancelled out, divided by 8.33 into 10 to the power 2, 1380. This is the answer. Basically, what does that mean? That means if you are having intrinsic semiconductor, to get the same amount of current, you need to use 1380 volt battery. And when you did the doping, after the doping, to get this much current, you just need 50 millivolt. So how much energy is saved? No, here there was so much power was here in this case so much power would be consumed, but here very less power is consumed. 50 millivolt multiply with 1 microampere, and here 1380 multiply with 1 microampere. So here 1380 microwatt power is used, and here in some nanowatt, here 50 nanowatt power is used. Just by the effect of doping, you are doing this much things, right? Are you able to understand this point? Okay, so that's why doping is useful for us. Very simple question, just you need to click. If you are able to click, then you will be able to solve. This was a gate PIQ question. Total electric field. Find out the total electric field. This valence band is given. It is having this kind of slope. Find out the total electric field. Electric field is equals to 1 by q dEV by dx. So what is the slope here? Delta by L. So what will be the answer? Right? Because the slope was dEV by dx. Here I can see the slope, that is delta by L. Okay, so if this is the slope, this is the answer. There you go. This is our end of basic semiconductor physics. Okay, we have seen more than enough question. Now your job will be you need to solve the PYQs. That's it. Now from this basic semiconductor physics part, 50% of the questions will come from EDC. Let's just say in EDC is coming of 8 marks, then 4 marks of basic semiconductor physics would come. So 50% marks are consumed from here only. Although this is the 40% of the syllabus, like 40% syllabus is completed. In EDC, 40% syllabus is completed, but 50% of the marks will be helpful in the examination. Okay, so it will be coming for 50% of the marks. So a major portion in a very easy manner we have done without remembering much of the formula, right? Formula remembering I wanted to reduce. That's why that was my major target. In EDC, people think that it is based on formula. This thing we need to remember, that thing we need to remember, and most of the times people will be just studying the concept. But there is an equilibrium between concept, formula, and the problem solving approach, and that equilibrium we have built up in this lecture, right? So basically, it would be of roughly around 9, 10, 30, 22.5 hours. In 22.5 hours, we have completed our basic semiconductor physics. And usually it would take, if you are not making your own note, if you are just studying from the lecture PDF, then it would take roughly around 35 hours to complete. If you are making your own note, then it can increase. It depends on your pace. But if you are studying from the PDF, then in 35 hours you will be able to complete basic semiconductor physics. And you go to any lecture, you would see the content will be of more than 40 hours. Content itself. Okay, and you let me know in these 40 hours, do you find anything new that I did not teach here? Like there will not be a single topic which they are teaching and I am not teaching. but needless derivation will not be there. Okay, needless derivation we are not doing, neither we are writing down the results directly. Like if I don't do the derivation, then what I can do, I can directly write down the result, that this is the electron concentration, that's it. I could have written down the result. For this there is a 2-page derivation for this particular formula. But did I directly write down the result? No. Directly writing down the result is also not good, and doing the needless derivation is also not good. What we did, we understood the importance of NC, we understood the importance of probability. Multiply both of them will give us number of electrons. So this is how we reduce the number of hours. This is how we build up our thinking, and this is how we prepare ourselves for the competitive examination. So in 22.5 hours we have done absolutely brilliant work. Your target would be to share it. What you need to do, only thing I expect from your side is sharing it, so that this content should reach to a lot of people. Okay, EDC this, EDC that, just see this thing now. Okay, so share it to the maximum. Okay, yeah, thank you very much. Notes and everything will be shared on the Telegram group. Yeah, thank you very much. Happy learning. Let's meet again in some other lectures.